Hey there, astronomy students. This is Miss Ruark. This is podcast 15.1, where we're going to start talking about the Milky Way. We're getting into galaxies now. Woo! All right, so um, the Milky Way. What is the Milky Way? Well, the Milky Way makes up almost everything we see in the night sky. And we see most of the Milky Way as a faint band of light across our sky, but if we were to look at it from the outside, the Milky Way might look very much like our cosmic neighbor, the Andromeda Galaxy. And this is an example of the Andromeda Galaxy here. Okay, and sometimes, not all the time, but sometimes when you look up into the sky and you see your constellations and your stars, you see a haze that kind of goes through, and that would be, well, the Milky Way. All right. So structure of the Milky Way. The structure of the Milky Way contains a disk, okay, which if you look at it from the side is flat. If you look at it from the top, it's the arms, the spiral arms that are coming out. It also contains a nuclear bulge, which is in the middle. The nuclear bulge is kind of thick. You see it's thick and it's bulky, right? All right, we also have the halo of the Milky Way, which is kind of like the gaseous stuff that's around the, if we looked at it flat, it would be the gaseous stuff that's around the top and the bottom. And then the globular clusters of stars, which are typically going to be in the halo. All right, so the Milky Way has a galactic plane, which is going to be, if we looked at it from the flat side, it would look straight across. Okay, galactic center is, it's in the center, right? Well, the structure of the Milky Way is going to be something that's going to be a little difficult to determine because, number one, we're on the inside. We're not on the outside. Number two, distance measurements are going to be difficult to make. And number three, our view towards the center of this galactic, of the Milky Way is obscured because there's a lot of gas and a lot of dust in our way. All right, so who is the first person to, or how did we start studying the galaxy? Well, it was first, the first study, I guess, of our galaxy would have been done by William Herschel, and he based it on optical observations. And he pretty much said that the Milky Way revolved, or that the sun was close to the center of the Milky Way, and he thought that the Milky Way resembled what they call grindstones. So a grindstone, example of that would be this right here, right? And a grindstone is pretty much a stone that's used, it's on a wheel, and you can use it to grind things or sand things down. All right, well, guess what? They found out that that's not completely true. All right, so when we explore a galaxy, we use clusters of stars to explore a galaxy. We've already talked about these two. We've talked about open clusters, which are young clusters of recently formed stars within the disk of the galaxy. And then you also have your globular clusters, which are going to be old, centrally concentrated clusters of stars, mostly in a halo, and that goes around the galaxy. Right, and in our globular clusters, again, dense clusters of about 50,000 to 1 million stars. They're old stars, approximately 11 billion years old. Lower main sequence stars. Lower main sequence, so they're not bright and they're not hot. And approximately 200 globular clusters. Sorry about that. There are approximately 200 globular clusters in our Milky Way. All right, so if we were to locate the center of the Milky Way. All right, so they found that the sun is not the center of the Milky Way. It's not the center of the galaxy. It's actually off to the side. What's the center of the galaxy? It's not centered on the sun, but it's in a location that's obscured. Didn't mean to do that. It's in a location that's obscured from direct observation. Why? Because there's a lot of dust, a lot of clouds, there's a lot of globular clusters, etc. Okay, so the center of the galaxy is actually there. All right, they have said that they believe that it is more towards the Sagittarius, out past, I think it's Sagittarius constellation. All right, so you can view the Milky Way from infrared images, and when you do this, because the interstellar dust is absorbing optical light and giving off mostly infrared light, you can see, you'll see the interstellar dust. However, and there's the nuclear bulge. All right. However, infrared emissions, they're not strongly absorbed, and they provide a beautiful, clear view of the Milky Way. And so here you could actually see a lot more because it's infrared as opposed to um, it's far infrared, sorry, as opposed to the near infrared. So it's different sides of the infrared. It's going to be stronger and less strong. All right, so some galaxies that are similar to ours. The Sombrero Galaxy is, I know, great name. It's gas and dust with light in other galaxies, and it has dark dust lanes when we see the galaxy from edge on. So it's kind of got this dust that just sits there and absorbs the light and doesn't let the light go through. All right, and then we also have this other one, NGC 2997. And if you looked at it from top down, you would see the dark clouds here in the spiral arms, and that's just the empty space or the dust, right, where the stars are not. Okay, let's see. When we explore the Milky Way with massive stars and open clusters, so O and B stars are the most massive, they're the most luminous. Unfortunately, they are also the ones that live the shortest life. Not good. All right, so we're looking for very young clusters or associations containing O and B stars, OB associations. These are going to be in open clusters, right? All right, massive stars in open clusters. What's the problem? Well, many stars in the field of the O and B association do not belong to the association. They're either foreground stars or background stars. Okay, so members of the association have been formed together. They're actually going to move in the same direction. Okay, so what's happening is these foreground stars and background stars aren't moving in the same direction. Not good. Okay, so you can identify the members of the association based on how they move through the sky. All right, orbital motion in the Milky Way. Orbital motion, disk stars are nearly circular in their orbit and in their orbit of the disk of the galaxy. However, we have halo stars, and they are highly elliptical, and they orbit randomly around the galaxy. Okay, so here's our galactic plane. The disk stars, the ones that are in the arms, are going to go around. The spiral arms are just going to go around in circles. But then we have these halo stars, which are out in the halo, and they just kind of randomly, elliptically go around the center of the galaxy. Let's see, orbital motion in the Milky Way. Differential rotation, which means that different levels of gas are going to rotate at different speeds. So the sun's going to orbit around the center at about 220 kilometers per second. One orbit takes approximately 240 million years. It's a really long time, y'all. Oh my goodness. Stars closer to the galactic center are going to orbit faster. Yeah. All right, and stars that are further out are going to go more slowly. Okay, well, think about it. They have the ones on the center have less space to cover, right? And the ones on the outside have more space to cover. So that would make more sense, right? All right, so how can we find mass from orbital velocity? Well, the more mass there is inside the orbit, the faster the sun has to orbit around the galactic center. So what's another way that we can say that? The mass of the galaxy can be found from its rotation curve. Right, and it has shown that the halo contains more mass. Yeah, but it's just a bunch of dust. It actually contains more mass than you would think it was. It would. All right, so combined gas for the sun would be 1 billion suns. And then going around really fast would be 100 billion suns. So the more mass there is inside the orbit, the faster the sun has to orbit around the galactic center, right? Think gravity. Okay, mass of the Milky Way. So here it's showing, let's see, if all the masses were concentrated in the center of the galaxy, then the rotation curve would follow a modified version of Kepler's third law, and you'd have this nice, pretty swooping graph here. That was really bad, but hold on, I gotta sneeze. Okay, sorry, I had to sneeze. Okay, but because the mass is not all concentrated in the center, we have a rotation curve, and that was cute. Orbital velocity is a function of the radius. So you see how you've got this nice It says the radius here, as the radius increases, the orbital velocity should increase as well, right? Well, notice it dips down real quick, but then it starts to pick back up again. Okay. All right, mass of the Milky Way, total mass in the disk of the Milky Way. Now think, disk is these outer spiral arms, is approximately 200 billion solar masses. Oh, that's a lot. All right, additional mass will extend into the halo up here, which is approximately 1 trillion solar masses. Whew, that's still a lot. Okay, so most of the mass is not emitting any radiation whatsoever, and we would call that dark matter. So the mass not emitting electromagnetic radiation is called dark matter. Ooh, scary. All right. Metals and stars. So metals and stars will be shown by their absorption lines. Okay, so stellar populations are actually going to be an important clue. Oh, goodness gracious, excuse me. An important clue to the formation of our galaxy. All right, the first stars to form, they were termed population 2 stars, and they were poor in elements heavier than helium, which means that they did not have metals. How did we know? Because you don't have absorption lines for anything but hydrogen. Okay. As generations of stars manufactured metals in a process called nucleosynthesis and spread them back into the interstellar medium, the metal abundance of more recent generations did increase. So now you have your population 1 stars, which include the sun, and they're richer in the metals. How do we know? Because their absorption lines show that they're heavier elements. Okay, how can you tell? Well, because look, these thick lines here, okay, yes, there's still helium, there's still hydrogen, but you have these other lines here that are going to start showing up, and those are going to be showing the other elements that are heavier. Okay. Let's see. At the time of formation, the gases forming the Milky Way consisted exclusively of hydrogen and helium, and the heavier elements were only produced later in stars by nucleosynthesis. Okay, what did that say? Young stars contain more metals than older stars do. Okay, the younger stars, because you have that nucleosynthesis happening, it's spreading out all that metal, all that stuff back into the interstellar medium. Those younger stars that are forming are now going to have more metals in them than the older ones will. All right, so stellar populations. We have 2 types. Population 1, those are going to be young stars, metal rich, located in the spiral arms and the disks. Okay, so where would they be? Spiral arms and the disk out here. Right, young stars, metals. Okay, oh, I didn't know I had the arrows. All right, population 2, you have your older stars, metal poor. They're located in the halo, so all this, the globular clusters out here, and then the nuclear bulge on the inside. Okay, there you go. Abundance of elements in the universe. So, as you can tell from this, the relative abundance of elements, there's a good abundance of hydrogen. Of course, there's going to be tons of hydrogen. As you go down, the elements heavier than iron are going to get, the abundance is going to get smaller and smaller. But there are more hydrogen, helium, and then the, I'd say heavier elements, but in comparison, they're really not heavier. Carbons, nitrogens, and oxygens, because those are in the universe and the stars that are fusing carbon, nitrogen, and oxygen, and your CNO, and then your iron. Look how your iron spikes back up. So see your other elements based on atomic mass, they get fewer and fewer, but then all of a sudden your iron spikes up, and that's because you're going to end up fusing those elements into iron, and you form those iron cores. Okay, and your element's heavier than iron. Well, there's not a lot of them. Okay, galactic fountains. What are these galactic fountains? Well, these galactic fountains are going to be produced by expanding supernova remnants, and they help spread metals throughout the disk. Okay, so multiple supernova in regions of active star formation produces bubbles of very hot gas. The gas breaks out of the galactic disk and produces a galactic fountain. As the gas cools, it falls back to the disk and it spreads those heavy elements out throughout the galaxy. All right, and we're done. So that's it for part 1. I'll see you later.